Welcome to Longevity Industries' presentation of the Destiny of Manufacturing podcast. I'm your host, Dean Phillips. I'd like to thank our sponsor, the Precision Metal Forming Association and the PMA's Educational Foundation, for all of their contributions to this show and all their great work within our industry. I'd like to introduce to you today Ed Neff. He comes to us from SMAC, where he is the president, and I'd like to introduce him right now. Ed, are you there?
Yes, I am.
Great to have you on the show. So,
Thank you.
Tell us a little bit about your background and how you came to be here, and tell us about your company.
Okay. Well, all right, the company's called SMAC. Comes from two pneumatic companies. One's SMAC. It's an air valve company in Detroit. It's my family company. And SMC, which is a Japanese company. And I worked for both of those companies. For MAC, in starting up a factory for them in Belgium, playing a lot of rugby over there. And then when I spent 7 years in Japan, winding up as a director of SMC. SMC went public. I made some money. I left, and I came over to San Diego and started up SMAC. And what we wanted to do was develop devices that act like fingers and hands, and then knock out the older technology, which was pneumatic, electric ball screw, and moving magnet stuff. And we started out by, we didn't know what we were going to do, so we started out by making assembly machines. First with pneumatic, wrote all the different things that we couldn't do pneumatically, developed our first devices, which are moving coil linear motors that could do things that we wanted to do, which was variably programmed positions, forces, and speeds, and be able to do some work and know that we did it correctly, so we wouldn't have to use sensors. So we developed that, then we stopped making machines and started making these devices and started selling them. The devices are mechatronic, and they're still unique because you can do things and know that you did them correctly. Mm-hmm. The big challenge for us was to get the price down. We started with $3,000 for an actuator and a controller, and we follow a process of reducing the price by 1/3 compared to the current products every 5 years. So we're now down at about $350 for an actuator and a controller from the $3,000.
Wow.
Which puts us about the same price as ball screws and about 2.5 times the price of pneumatic. And we do this by making our own encoders, making our own controllers. These are moving coils, so we used to wind the coils. We now print them, so that's much cheaper and knocks out lots of connectors and things. We're making some of the guiding mechanisms ourselves. Those are flexures instead of using linear guides. And that's a big cost down. The next thing up is to go after the magnets, knock the heck out of the cost there. So we can get down to 1.5 times the price of pneumatics. The actuators are the fastest around. They're twice as fast as anything because moving mass is so light, and they last hundreds and hundreds to hundreds of millions of cycles, which is much longer than pneumatic or ball screw. Moving magnet linear motors also last a long time. So that's pretty much the set. We sell 1/3 in Asia, we sell 1/3 in Europe, 1/3 in North America. Customers were in electronic assembly, consumer electronics, a lot of automotive for quality and measurement. The big area for us now is packaging because we're cheap enough to knock out pneumatics on a fair number of applications. And we're also now moving into lab automation, which is submicron movement kind of devices. The company's about 250 people. Sales are over 50 million, and we're growing about 35% a year. About 250 people in the company. About 50 of them are engineers. And we got about 35 sales tech support people around the world. So that's kind of. I hope that was 5 minutes and sums up us.
Well, that's great. That's amazing. That's an amazing story. And I'll tell you, I think there's a lot of companies out there that wish they could get their prices down in that simple of a description. I think that
yeah, it's fun. It's fun doing it. You can, I learned a lot of that over in Japan by the guy who started SMC. He always did that. I learned a lot from him.
That's great. That's fantastic. So tell us, as the show is the Destiny of Manufacturing, tell us what your vision is of where we're going to be in 5 years. How is automation going to help us? How are we going to be changing our outlook?
Well, there's a lot going on in robotics, right? That's really jumped. So whether it's devices that look like us or devices that pick up and move around and put in, there's more and more of that is becoming cheaper. So that you're going to see a lot more robotics. Where we fit in, we're like fingers and hands, and you don't see that much. Robots you see right now don't really have fingers and hands. They have arms,
right,
legs, but not fingers and hands. But when you have all these things together, there's less and less need for people, right? So the automation process is going to speed up. And as more automation takes place, quality goes up, right? Because the robots don't miss, right? So that's what's going to happen. Like, say, an example in California, the minimum wage is moving up to $15 an hour.
Right.
Well, the automation projects that are going on in fast food are amazing. All because of that cost.
Sure.
So it's just going to be more and more robotics.
Right. Now, as part of that, I know that one of the concerns that many companies have is learning the systems. How do I program this? And what do you see changing in order to accommodate that?
Oh, there's a lot. Well, initially a lot of GUI development, right? So for example, we make automatic thread checking and automated capping systems, and it's all GUI related. So you can set up and run something without having to program, right? It's just, you're saying go down to this point, do this move, do that, report back this. So it doesn't require machine language programming. So there's a big front end on it.
Sure.
So that's the thing that's going around right now to make it easy. So you don't need really detailed programming capability. That's done for you.
Sure. And now that was one of the concerns that I'd heard from several different companies was the ease of programming and where that's going. And it sounds like
the GUIs take care of it because we have four fellows full time that are working on GUIs. So you have different apps like we're trying to do smart screw driving where you can take a screw and put it down, rotate it counterclockwise so it finds a center, and then drive it down and report everything. And then you have somebody doing the GUI, so anybody can take one of our smart screwdriver devices and have it up and running in less than 20 minutes.
Wow, that is outstanding compared to where I know it used to be. It was days of programming. Not.
Oh yeah. When we started doing machines, special machines, that's how we started. Special assembly machines.
Right.
You'd be programming, but now there's this, with the GUI interface, it's easy.
Oh, great.
Everybody's doing that.
Yeah. Now I've seen that one of the things that, especially from the stamping industry side of things, is integrating the automation with stamping operations or in-die mechanisms. What do you see or project that will be changing in that area?
Okay, well, that's interesting. There's a lot of smarts going on. I don't do stamping. I got a buddy in Indiana that has a stamping operation. He's missing 2 fingers, which is normal for those guys.
Sure.
But for example, here we're doing something similar. We do a lot of extrusion. Okay, and this is plastic extrusion, and you always had a die in a mandrel, and you set it up, and you're trying to center everything. Well, and that's done by 4 screws that center the die, and it's kind of like, holding down a Christmas tree trunk. Well,
Right.
We put our own devices in it now, and they got 0.1 micron encoders in it, so you can automatically adjust the center down to submicron level, and you can include the process feedback, so you're continually making adjustments and holding it dead center. There's a lot of stuff going on that's in process in process control where you can chop the tolerance variation down by 2/3 and center it. And if you have it 2/3 and centered, then that's it. You're never going to be out.
Yeah.
That's going on in lots of different manufacturing applications.
Yeah, that's a great way to approach the tolerance and dealing with a high degree of accuracy applications.
Yeah, and then in terms of we're doing that. We've done that with all the smartphone guys, makers with their lens assemblies, which are 8, 10, 12 piece press fit assemblies on the lenses. Mm-hmm. And you pick up a part, you know where it's going to go. You land on top of another part, you know where that is within a micron or two. You apply a correct force for watching as it moves in, and you stop it exactly where it's supposed to stop. So you've taken we did the famous Korean guys and their lenses. They had 30% scrap using pneumatic where there's no feedback. Put our stuff in where there's feedback, and you control all the different variables. And the scrap went to 2%, and that's because the parts were bad, not the assembly process.
Wow!
And that's going through everybody's is picking that up now. That kind of in-process control and knowing what's going on.
Wow, that's great. Do you see that adapting this technology to using vision systems to help close that loop, so it's not just the encoder aspect, but because somebody might say yes, the accuracy is important, but I need to just know that it's there for part verification.
Well, there's times you use vision, and then there's times you use tactile. Okay.
Sure.
And like for example, here's a vision one. You have we make encoders, and we have on rotary encoders we have a disc, and we've got to center the markings on that disc within 2 micron, so you don't get a wobble. Right. And so that's a camera application, because there's a hole in the center of the disc that has no relationship to anything. Right. But you got to glue that disc in the center. So you use the camera to find 3 fiducial points. 2 is enough, really. You get your arc, and now you know where the center is, and you can set that thing down. Those are fingers that have to, robotic fingers that set it. But there's a combination, because the camera sees the fiducial, right? Mm-hmm. Or you use lasers. We use lasers to measure tubing, right? You can't use it. You can't go tactile on that because it's soft. You'll damage it. So there's all sorts of places for cameras. There's all sorts of places for lasers, and there's all sorts of places for tactile, for using hands and fingers.
Right. That's great. Do you think that that we're going to see more and more of these sensor systems? Because I know that's been a big part of what people have talked about is increasing the number of sensors in different applications and trying to.
The ones that they're being built into the devices that do the work. Right. So 15 years ago, even 10 years ago, you'd do something, and then a sensor would look at it. Right. Right. That'd be a secondary operation. Like assembly machines, you'd take one part and put it into another, and then a sensor would pick up. It could be a prox, it could be a through beam or whatever. But it would pick up the edge of the part to say, "Yeah, hey, I got that, and it's there." Right. But now it's gone beyond that, because the sensors are being developed are in the devices that do the work. So as you do the work, you're reporting back in real time what's going on. So it's not like a secondary op. So more and more, it's mechatronic. More and more of the devices that are doing the work have the sensors built in, and there's continuous feedback, so you know what happens.
Right.
Like we put caps on. We're starting. One of the big new apps in packaging is capping. And that's we have a device that goes up and down and rotates independently.
Mm-hmm.
We'll take a cap, and we'll hit the top of the bottle softly. It's a soft land, we call it. Go backwards, threads match, drops down about 50 micron, 100 micron. Now you're not going to cross thread. You're driving down. You're monitoring the torque it takes as you turn. You're monitoring the distance you traveled, the number of turns, and then you snug it, kind of like you do when you change a tire with the bolts.
Mm-hmm.
Set a 0, hit a torque, make sure it moves X degrees. So as you put the cap on, this is all going on within a second. You've done you've fed back 6 different things that says, hey, this thing was done right? And there's more and more of that in industry.
Right. I think for the audience that's an area that is often overlooked, that when they're talking about actuators and motion in general, they get all caught up in just the aspect of distance and measuring positionally. But I think when you talk about torque, that adds a whole different other dimension to things, because as things deflect, you're not just dealing with just positional issues, you're also dealing with deflection and other aspects that also can come into play, and measuring that can be just as important as actually measuring the position.
Yeah, you want to make, if you ever, when you put the cap back on your toothpaste, you do what you rotate backwards to match. Most people do that, and then they run it through. So you're doing what the devices are doing what humans do.
Right.
But the feedback is so much more precise.
Right.
Right. And that's an interesting thing. One of the big apps for us in the beginning still is we make a lot of the pick and place heads that are on circuit board assembly machines. Mm-hmm. And what you're doing there is, they'll have on the actuator, there's a laser and a camera, and it'll, depending on the part, it'll look at the part. It already knows where it's supposed to go. It already has looked at the contacts on the bottom of the chip, and you're going down and you're making a positional change in data rotationally, so you make sure that all the contact pins, which are bent to one way or another, hit the pads correctly, right? So there's all sorts of detailed stuff that's going. Usually it's electronic assembly that's leading, and then the other industries like packaging or your stamping, that kind of stuff, they pick up what's developed in the electronic side, because the electronic side, you can't miss.
Right.
You got 2,000 chips you got to put on the board. You miss one, you just wasted the board, right?
Yeah. And you're not even talking about the size chips that we used to deal with. We're talking about chips that have about 500 pins and are half.
Or they're very small. We're just out we're selling in Japan, where initially it's big. You have little grippers that have a pickup force of like 5 grams or 1/6 of an ounce, right? Because the parts are so small, you can't use vacuum and pick them up.
Right.
So
right.
It's interesting in how the electronic assembly industry drives all that, so much tech.
Sure, and it certainly makes sense too. Tell me a little bit about what technology areas do you see changing the most in response to automation?
What technology areas do I see changing the most? Define technology area for me.
Well, I think, is it, do you see more in the sectors of lasers, or and I'm not speaking of lasers from the usage standpoint, but in building lasers and manufacturing of the lasers themselves, or manufacturing, doing things like forming and fabricating, or even in some of like the things now with 3D additive printing and stuff like that.
Okay, there's a lot of if you consider the word composite, right? I mean, there's all sorts of different ways of fabricating things now with all sorts of materials. that are much different. I'll give you just a simple application for us. We have all these winding machines for winding coils. And most companies, if you're going to come up with a new coil that's volume, you're spending $250,000 on a winding machine, special winding machine to do some kind of thing. And you get, companies that have, some of the companies that I've worked with, or I've worked for, have, 200 people in Taiwan or 1,000 people in China running all these different winding machines with, tens of millions of dollars investment. Well, with the new technologies, like flex circuit technology and that kind of thing, you can print these coils. And you can do all sorts of configurations that you can't wind. And the cost is like 20% of a wound coil. And you could print 10,000 a day in a 500 square foot room. And just wipes out all that old, electromechanical technology, right? There's all sorts of stuff that's coming up because of new processes and being able to use different materials that really change things.
That's an interesting way to look at it.
I can sit here in Southern California and print more coils in a small room than 100,000 square foot factory in Beijing, right?
Right.
With 5 people, because of the new technologies.
Right. Do you see more applications coming up in the 3D printing areas? Like
it's interesting. If it's a small quantity, it's great, right? Like I played football and a lot of rugby, and I have a left knee that doesn't work very well.
Right.
And the companies that are making these now are scanning and using 3D printers and coming out with instead of like one, 3 sizes fit all.
Right.
It's exact. It's exact to fit your knee.
Yeah.
So if it's onesie twosie, that 3D printing is good. If it's 100,000, it ain't so good.
Right.
But you can do things with 3D printing that you can't do with anything else. And the materials that you can use that's expanding rapidly, right?
Yep.
In 3D print.
Do you see more desire from manufacturers to somewhat? Now we talk about closing the loop, and when you're talking about actually monitoring what the actuator's doing, that closes that inner loop. Then the next outer loop of the equipment that the actuator is going on, do you see a desire by the manufacturers to say, hey, can you monitor this also and the next level out?
Yeah, everybody's tying in. There's, it's I don't want to plug these guys, but there's communication systems that are really powerful. In the U.S., it's Ethernet IP, right? In Europe, it's EtherCAT,
right?
And that's tying everything in. And so we make our own controllers, and they're really small, really inexpensive. We just came out with a new one that's really cheap. Size of your fingernail. But inside it's got that communication protocol.
Right.
Because you have to tie into, you might have a manufacturing system that has quality measurements and has timing and on-the-flight program adjustments, right? And that's all, so all the elements that the sensors, the actuators, the robots, whatever, they have to all merge and be able to communicate to each other. So that's going on more and more and more and more and more.
Right. And do you think that's one of the biggest challenges, getting all these things to talk to each other now? No, it's moving ahead pretty well. Yeah.
It's going faster and faster. So you got to be able to. You need to have a firmware capability in your company. Got to be able to develop. You have to be able to develop your own firmware if you want to track these fellows.
Right.
So that's for you. That's required if you're making something that's smart.
Yeah. Ed, I hate to tell you this, but we are out of time.
That's okay.
I really do appreciate it. Thank you so much for spending time with us today. It's been incredible. It's been great to talk to you.
All right. Well, it was good to talk to you. I think I've never talked to been interviewed by somebody from Nashville. I'm not sure I'm allowed to say that.
Yes, you can. It's not a problem. And we'd like to thank our sponsor, the Precision Metal Forming Association and the PMA's Educational Foundation, for helping us put this on. Thanks, everybody. Have a great day.
Okay, thank you. Bye.
Bye.